absorbing Markov chains. Consider a Markov chain with n different states, and that's basically what we've been doing already. The ith state, S of I, is said to be absorbing state when in the matrix of transition probabilities P, Pii is equal to 1. That is, the entry along the main diagonal is 1. So, and then all other entries in that ith column of P where there does occur a 1 on the main diagonal, there's zeros elsewhere on that particular column. Now, this matrix is not the identity. It's just talking about maybe having 1 or 2 columns that may look like that. An absorbing Markov chain has 2 properties. One, the Markov chain has at least one absorbing state. Remember, the state is a column. It is possible for a member of the population to move from any absorbing state to from any non-absorbing state, to an absorbing state in a finite number of transitions. You remember before when we had the problems and I drew the bubbles and said, we got this state here, got that state. That's what they want you to do, and then you draw the links. How do you get from one state to another? And so what they're saying is that, is there a link from a non-absorbing state to an absorbing state? Basically, how can I go from one column that has several entries in it to the column that only has the zeros and the 1? Is there a link? It's interesting because this same concept, this is probability theory, but the same concept in vector analysis is considered around the same time that we introduce Green's theorem. We talk about a region, and then even after Green's theorem, trying to build Stokes and the divergence, we talk about a connected region. Same thing, folks. Same concept. Pretty cool stuff. Well, let's see. If you look here for this matrix, notice that the state 1, state 2 and 3 where we're coming from, and then where we're going to state 1, 2, and 3. But the key is to look at the columns. Now, what they're going to do is to show you here for this matrix represented by the second column is an absorbing column, right? Because that's where you have the 1 on the main diagonal and zeros elsewhere. Moreover, the corresponding Markov chain is also absorbing because it is possible to move from S sub 1 to S sub 2 in 2 transitions, and it's possible to move from S sub 3 to S sub 2 in 1 transition. I cannot see that based on that. I have to see those bubbles, right? So based on what they're giving us here, you cannot see, I know I can't, how to get from one transition to the other. Let's look at this. So again, going back, S sub 2 was the state that is absorbing. So how can we get from a non-absorbing to an absorbing state? That is, can we go from S1 to S2, and can we go from S3 to S2? So now, look at this. So, can I go from S1 to S2? Yes, but it takes 2 iterations to get there, right? And then, can I go from S3 to S2? Because S2 is the absorbing state. S1, S3 are non-absorbing. Yes, I can get there in 1. And when I'm drawing these lines in connectors, I can't do this because there's no connection. I'm actually following here, right? I'm following what's there. So that's what they're talking about. Okay, let's look at another one. Here, notice that S sub 2 is said to be the absorbing state. Now, is it possible to go from S1 to S2 and then also from S3 to S2, S4 to S2? Well, here they say that this is not an absorbing state because there's no way that you can get from S3 or S4 to S2. Again, let's look at the chart diagram to see if we can make that connection. So let's go back. So S sub 2 is where you want to get to. So I'm trying to get to S sub 2. S sub 2 is here. Can I get from S sub 1 to S sub 2? Well, yes, we can. Yep. Can I get from S sub 3 to S sub 2? No, there's no connection. Can I get from S sub 4 to S sub 2? No. So now you see why this is non-absorbing. And here's another example. Again, now here S2 is the absorbing state. So let's look at the diagram. So I can go from S1 to S2. I think S2 was the, yes, S2 is the absorbing. So I can go from S3 to S2, S1 to S2. It's possible to go from S1, let's see, to S1 to S4. Let's see. I don't see going back from S4 to S2. He says it. Oh, I'm sorry. S4 is already absorbing, so that's right. Good deal. I didn't see that. So S4 is absorbing. So I can get from S1 to S4, S1 to S2, S3 to S4, S3 to S2. As long as you can go from a non-absorbing to an absorbing. Ah, we got it. Cool. Cool. The process for finding a steady state matrix for an absorbing Markov chain is the same as before. What do we mean by same as before? Here we still solve P times X is equal to X to find the steady state, and you remember also we have to solve X sub 1 plus X sub 2 plus and so on plus X sub n is equal to 1. Yeah. Okay. So let's see. And this is the last problem. And also this is the last problem in the homework, which this problem was somewhat of a challenge. And so let me work it out, and then you'll be able to, to work it out when you get to it. And let's see. It says here, in a population of 400,000 people, 40,000 are infected with the virus. After a person becomes infected and then recovers, the person is immune to not become infected again. Of the, let's see here, the people who are infected, 5% will die each year, and the others will recover. Of the people who have never been affected, 40% will become infected each year. How many people will be infected in 4 years? Round your answers to the nearest whole numbers. So we got to have a bubble for the people who are infected, right? And then we have a bubble for the people who have never been infected. I guess it'd help to know how to spell infected. Inflected? I know about that word. I'm still trying to write it. Acting like I'm inflected. So then you got this group here. Some are dying, and then it says that you have some that are recovering. Right? So let's see. It says, well, it gives us the definition that after a person becomes infected and then recovers, that person is immune. Of the people who are infected, so we're here, 5% will die, and then it says, and the remainders will recover. So we draw an arrow, and that says here 0.05, and then the remainders will recover 0.95. Okay. Of the people who have never been infected, 40% will become infected each year. So that's the arrow going there, 0.4. Right. Well, if 40% of the people who've never been infected get infected, then other people who've never been infected, if 40% is being infected, then how many is not being infected? 60%. So that's coming right back to you, 0.6. That guy got me, that last part right there. And so I don't know, I didn't see it. And so, when you're doing work like this and you don't have any example, or you can Google, even I could Google stuff and find out, how to work it, but that's not helpful. If I suffer through it to get it, I never forget it. So, let's build this matrix P. So we have the people who are infected, the people who never, people who die, and the people who recover. Need a little bit more space. Infected. This is never shorthand. Die. Ike Clanton in Tombstone. I hope you die. And then this is recover, R-E-C. And then here this would be, just going to use that same chain. Infected. Never. Die. Recover. All right. So of those who are infected, 5% will die, so 0.05, and then 95% recover. Right? It says nothing about these two. That's 0. Those who never been infected, 40% will become infected, so that's 0.4, and 60% will stay, not infected. Right, so that's 0.6. Now that's already added up to 1, so this is 0 and 0. Same thing here. These two added up to 1, so the other two have to be 0. Those who die, well, they can't get infected, and those who die, they can't just never have it because they're dead, right? And if they die, do they recover? No. If they die, they stay dead. That's 100%. I know that. They're dead. They're going to stay dead. Okay. Anyway, those who recover, let's look. Those who recover, we have everything coming to it, but there's nothing going from it. So here, those who recover, they don't get infected. Okay, 0 for never. They recover, so they don't die. So they recover. It's 100% probability. Once you build that, I mean, everything else is like just downhill. But that crapping, stupid transition matrix right there, man, make you sick. So we're looking for here what happens in 4 years, right? So x sub 4 would be that matrix P raised to the 4th power. I'm not going to write that back over, but that's the matrix P raised to the 4th power, and it's times, you got to have the initial state, that's times x naught. Now what is x naught? X naught would be how many people that are initially infected. It says 40,000. And then how many people of the 40,000 who are not infected? 360,000. And then I'm going down this order. How many that dies at 5%? So 5% of the people who are infected. So 5% of 40,000 is 2,000. All right. And then how many that recovers? So it says if you got 5% who die, then the other 95% recovers. So that's 95% of the 40,000. Basically, it's just 2,000 from 40,000. You get 38,000. So this is the initial state. Those who are infected, those who are the nevers, those who die, and then those who recover. So now what you're going to do is you're going to simply put this information in your graphing calculator. Take this matrix P, and you're going to raise that to the 4th power. Let me just put another slide in here and just write that out real quick, and then we'll be done. So here I have x to the 4th is equal to that P to the 4th times that initial matrix. So this is 0, 0, 0.05, 0.95, 0.4, 0.6, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. That's raised to the 4th power. And then this is times the initial state, 40,000, 360,000, 2,000, 38,000. And when you work that out, you get, I got this on the calculator, 31104, 46656, 18112, and then 344,128. Now let's see. Now these are the people who will be infected in 4 years. People who will never be infected in 4 years. It's the total number of people who will die in 4 years. And then the number of people who will recover. Now, the only thing that this problem asked for was how many would be infected in 4 years, and so that's the only answer that you want to give there, right? So that's 31, 104 of the, and it said how many would be infected in 4 years. Just want to make sure we were definitely answering that. Now, the good thing is you get a whole lot more than what's asked for, but you also get what was asked for. Does that make sense? Okay. That's Wes Harris. He likes to ask that question. If you have, take him for, I think, world religion. Does that make sense? Anyway, he heads up our technology department as well at the college, and he's a good man. Well, thank you, and we'll see you around.